Have you ever wondered how the sun produces energy? It's actually a process called fusion, a process that combines two light atomic nuclei to create a heavier one, all while releasing an incredible amount of energy. It's this very process that powers the sun and other stars. And it holds the potential to provide clean, abundant energy right here on Earth. So, how does fusion work, you ask? Picture two nuclei getting close enough together that the strong nuclear force between them overpowers the electrostatic force pushing them apart. This can only happen under extremely high temperatures, typically around 100 million degrees Celsius. That's hot enough to make the nuclei move so rapidly they overcome their natural repulsion and collide. When these two nuclei collide, they fuse together to form a heavier nucleus. This fusion process releases energy because the total mass of the resulting nucleus is slightly less than the mass of the two original nuclei. This difference in mass is converted into energy as described by Einstein's famous equation E equals sine m2. The most commonly studied fusion reaction for power production is the deuterium-tritium reaction. Here, a deuterium nucleus, a hydrogen nucleus with one proton and one neutron, fuses with a tritium nucleus, a hydrogen nucleus with one proton and two neutrons. The result, a helium nucleus with two protons and two neutrons and a neutron. This reaction alone releases an impressive 17.6 million electron volts of energy. But harnessing fusion power is easier said than done. It requires creating and maintaining the extraordinarily hot and high-pressure conditions necessary for fusion. Scientists are exploring various approaches to achieve this, including magnetic confinement and inertial confinement fusion. Magnetic confinement techniques like tokamaks and stellarators trap the hot plasma where fusion occurs using strong magnetic fields. These devices can achieve the necessary temperatures and pressures for fusion, but they still struggle to sustain fusion reactions long enough to produce net energy. Inertial confinement fusion, on the other hand, uses lasers or other high-energy beams to compress a tiny fuel pellet to the point where fusion occurs. This technique holds more promise for generating net energy, but it remains in the early stages of development. While there are certainly challenges to overcome, scientists remain hopeful that fusion power can eventually become a reality. If successful, fusion could provide a clean, safe, and virtually limitless source of energy for the world. An exciting prospect indeed.